My name is Hazim Gaber, and today we're going to have a brief introduction to talk about how the internet works. And the reason we're going to just jump into this topic is it'll give us a good background into the rest of the material. So, when you're thinking, when somebody says router, you think about the router that's in your house. This is probably what you think about. And this is a router, but it also performs many other functions. So typically, you've got either fiber coming into your house, or you've got the coax, or a phone line. And this thing gives you internet. But what is it actually giving you? Like, is Wi Fi. So I'm going to find out that this little box does a whole bunch of things. It's a modem, a firewall, a router, a switch, a DHCP server, a wireless access point. Now, in an enterprise network, this would be 6 separate devices at least. And we're going to find out why. So let's pretend, and I just took some random models. Some I like, some I don't like. But let's say this is our enterprise network. So now we've got the internet, which is on this side, which is the cloud. And we're going to look at what this cloud is later. But let's say right here in your office, you've got a computer. And you've also got so you got a PC and you got a printer. And you've got a laptop. And the laptop is wireless. Printer is hardwired. And then so internet comes into your office. Again, it could be a coax, it could be a fiber. And the first thing that happens is it hits the modem. What the modem does is it converts the signal that might be an analog signal, might be a fiber optic signal, into call it Ethernet signal. So the modem's job is to convert the signal. And there's a lot of the reason an enterprise network separates the function of each device is because every device has, we put everything into one device, that device would become overloaded. So we build enterprise class devices to handle one task and to handle it really well. So the traffic hits the firewall, and the firewall decides whether this is good traffic that passes through or bad traffic. And then the traffic hits the router, and the router, in this case, figures out who in the network is supposed to receive it, and it sends it to the switch. It addresses it to the internal network, and then the switch sends it out to the correct device. So let's say you get an email. Email comes in to your local network, passes through the modem, passes through the firewall, gets to the router. The router looks at the destination of the email and it sends it, say, to your PC right here. Or say you're on your laptop, it sends it through the Wi-Fi to your laptop. And how does it know? Because your laptop has an IP address. And the printer has an IP address. And the PC has an IP address. And the router has at least an IP address. The router, we're going to get into this later, but the router has an IP address on the inside and an IP address on the outside. And we're going to learn why. But effectively, it'll make more sense to say we also have a switch. And we also have a wireless access point. So, say I'm on my PC and I print a document. The PC sends a message to the printer, and that uses the IP address of the printer, and that hits the switch, and then the switch says, oh, well, the printer's on this port, I'm going to send the traffic here, and then you print the document. Now, the router's not involved, technically. Or the PC says, hey, I'm going to send a message to the laptop. Well, the laptop's on Wi-Fi, so the PC sends a message to the switch. The switch says, hey, the laptop's connected to the Wi-Fi, which is on this port. I'm going to send it to the wireless access point, and then the wireless access point sends a signal to the laptop. Or PC says, I'm going to send a message to somebody way out in the internet. So I'm going to address it to the router. And then the router is going to take that message and send it out to the internet. And so technically your PC sends a message to the switch. Switch says, oh, it's addressed to the router. Well, the router's on this port. I'm going to send it to the router. And then the firewall decides if it gets through. And then it's converted into a signal and it goes out to the internet. So the idea is that you have an internal network and an external network, which is the internet. And the router allows traffic to translate between the two. So a person on the external network can't address, say, your printer from, otherwise every device on the internet could talk directly to every other device on the internet. And in order for that to be possible, we'd have to have one big unsecured network, and we'd run out of addresses. So what you're going to learn is that there's a limited number of IP addresses, and the external addresses are all unique, but the internal addresses are only unique within that network. So if, say, your neighbor could have the exact same network and the exact same switch, and his computer could have the same address as yours. So say your address is 192.168.0.5 and your router's address is 192.168.0.1 and your printer is 192.168.0.4. Let's say that's the case. And your neighbor has a printer. Your neighbor's addresses are the same. So if your neighbor decides to send a message to your PC, he's got to send it to his router, and his router will send it to your router through the internet, and then your router will readdress it back to your PC. Because if he tried to send it to you using his internal address, or he'd have to know your internal address, which is impossible. Of course, you can, if you really, really wanted to, you could plug your computer directly into the modem, and then you'd have an external address on your computer. And then anybody on the internet could talk directly to your computer. So in that case, there's no router on your side. Now we're going to get into this in more detail later, but this is the gist of it for now. And now we're going to look at, so say if you look at the map of Canada and the United States, I'm going to pretend, now how does traffic get from one place to another? So let's say this is your office and I'm in California. I'm not, but say I'm in California and this guy's in Washington. So if you want, think about it, the internet is a big bunch of wires, big bunch of fiber optic cables that run across the entire, so they run across Canada and they run across the United States and they kind of zigzag, and then each fiber is owned by a different person. So, and then we've got fibers that go under the sea. Actually, they come out from Newfoundland. And so let's say that this fiber, red, is owned by a Canadian company called Palace. And then this fiber here, which is yellow, maybe it's orange, owned by Windstream. And then this fiber here is Verizon. And then whatever color this is. Let's say. And then purple equals AT&T. So imagine this X here. This is your router. So at every connection point, there's more routers. And these are big internet service provider routers. So change it to black. So if I zoom in, say, to one section, we got, so these are typically downtown, or they might be in random places, but let's say what you'll get is a room where the fiber comes in, and then fibers from multiple service providers. And so what did I say? This was Verizon. Let's go back to this. And so all these lines, these rooms are called points of presence. And they're all over Canada and the United States. They're all over every country. And basically, all the local service providers in that area bring their lines together, and then each one puts a router. So we put a router here, and I put a router here, a router here. Say this guy is Comcast. And then they all connect to each other. So Comcast connects to Windstream, connects to Verizon, connects to Thales, and then Windstream connects to Thales, and Windstream connects here. And this guy connects here. And that covers it. So let's say this guy, let's say Comcast, has a customer that's got a message, and he's sending it to Thales's network. So if you look, or for example, got a guy up here on the Thales network up in Canada, he wants to send a message to a guy on the Verizon network here in the United States, or the Windstream network. So in this case, the traffic leaves your modem, which we saw earlier. So it's left your modem and it's gone into the cloud, or i.e., it's gone to the first router. So the first router that it hits belongs to Thales, and it's right at the starting point. That's a router that talks to Thales customers only, or to the internet service provider's customers. And so it gets the traffic and it says, well, where is this supposed to go? Well, it's supposed to go all the way to Washington. So I better think about what's the best route. So a router does, it picks a route, and it's got a huge table, because this is actually way simpler than, I mean, my drawing is way simpler than reality. There's tens of thousands of pathways. So every router knows a few routes. So it says, well, if it's going here, so if it's going to California, it's going to take a different route than if it's going to Washington. And so let's say we had another customer, for example, here in Ontario. So if I'm up here in Canada, Western Canada, and I sent some traffic to Ontario, Eastern Canada, Thales router would say, hey, the best pathway is on the Thales network, and I'm just going to send it down Thales network, and boom, it's there. So the router made that decision. And there may be more. Obviously, the Thales network is complicated, so there's millions of destinations possibly, and so there's tens of thousands of routers along the way. But every router, but the first router that your traffic hits doesn't plan out the whole route. It just knows what we call a next hop. So the router says, oh, its final destination is here, so I better send it this way, for example. And then the second router says, oh, final destination is here, I better send it this way. So every router in the pathway makes a decision. So going back to my example, if I'm in Vancouver and I'm sending traffic to California, Thales router says, oh, he's going to California. Well, what's the best route? Well, I better say right here. I'm gonna give it to Windstream network. And so it ends up in one of these uh, points of presence. So the Thales router says, hey, Windstream, I got some traffic for you. It's destined to California. And then Windstream's router says, okay, destiny is California. What's the best pathway? Well, it's on the Windstream network, so let's keep going this way. And you can see that if I wanted to send it to Washington, I could do, it could probably pick, I could probably draw out 10 different pathways. I could go through the red Thales and then switch to AT&T and then Verizon for a bit, or I could go through Thales for a bit and then switch straight to Verizon's network, or I could go through Verizon's network and then hit Windstream's network. So if I sent a lot of traffic, they might not all take the same route, and that's because there can be congestion along our network. So routers have next hop. So I say, hey, this is my destination. This is my final destination. Where should I go? And also, there's what's called waits. So there may be 2 or 3 pathways that the router knows about, and the router can rank them based on how fast they are or other reasons. And then our, depending on how the network is functioning that day, they may choose, for different destinations, weights may change throughout the day. So sending it through Verizon's network might be good in the morning and bad in the evening, or good now and bad 10 seconds from now. And that depends because somebody else on some other network may have dumped a ton of traffic on Verizon, and now Verizon's network is slow, and so we're going to pick a different route. So this is happening trillions of times per day all over the country. There's traffic, and everybody's deciding where the traffic goes. And it's mostly the function of the routers, and there's routers everywhere, all over the country, and the routers help connect different portions of an internet service provider's network, and they help connect different internet service providers' networks to each other at the points of presence. And the points of presence are very important. Now, the next thing that we need to think about is called DNS, or Domain Name System. So remember that every, I'll go back to the map again, but every device on the internet has an IP address, everything that's facing. So say my computer, say this is Google's server, and the address is 8.8.8.8, and my address is 3.4.5.6. So how do if I type google.com in my address bar, how does my computer know what address I'm looking for? Because my computer can't tell a router take me to Google, because it was going to be like, well, who's Google? You know, what's the IP address of Google? And so I don't know. So now there's a massive phone directory called the DNS, and it's got Google, Microsoft, and it goes on forever. Every single website. So, and the DNS there's a bunch of main DNS servers. I'm gonna learn about DNS later in more detail, but basically your computer knows. So one of the most popular DNSs is 1.1.1.1. So your computer knows it's pre-programmed 1.1.1.1, or whatever DNS is pre-programmed to. And so it says, hey, tells the router, should say, send a message to 1.1.1.1 and ask it where google.com is, or where microsoft.com is, or where CNN.com is. And then the DNS server looks up here and says, oh, well, google.com is at 8.8.8.8. And then the computer says, okay, thank you. I'm going to send a message now to 8.8.8.8. So it tells the router, I want to go to 8.8.8.8. And then we end up with traffic on Google. And then if you look back later, your computer will remember now that Google is at 8.8.8.8. So it'll keep a record. Google.com 8.8.8.8. So next time it wants to go to Google, it doesn't have to look up the address. It just says, oh, I know where that is, and I'll just send a message. And then, of course, Google.com could change its address. So tomorrow it might be 9.9.9.9. So Google will update the DNS servers and say, hey, my address changed. And then the DNS will change the record. And then if I try to access the website again, now at 8.8.8.8, it will be broken. So I might say, oh, it's broken. I better ask the DNS again. Or we might set an expiry, so maybe 24 hours or 72 hours, and say, check this again in 72 hours. And that helps us so that we don't have to keep track of wrong information for too long. And then the real question is, who decides what number you have? So who decided that Google got 8.8.8.8, and that was a company called the Internet Assigned Numbers Authority, which sets IP addresses, and the addresses range from 0.0.0.0 to 255.255.255.255. And if you think about it, that's a lot of addresses. It's 255 times 255 times 255 times 255, which is 4 which is 4 billion addresses, right? Which sounds like a lot. And now you think that we have 7 billion people, and everybody's got at least one phone, one PC, maybe work phone, plus surveillance cameras and doorbells and etc. So this doesn't seem like a lot, such as why we have, going back to our early example, we have internal addresses and external addresses. So the 4 billion, really, in your house, you can have 4 billion addresses when you have one unique external address. So the whole internet, so you can think of your house like its own autonomous zone. As long as every external address on the whole internet, so company, so as long as every external facing device has its own unique address on the internet, and everybody can talk to everybody, because I don't need to know. This company might have 20,000 computers on its network, and I don't need to know the address to that computer. As long as I know the external address of that company's network, I can send the traffic. And the router the edge of that company's network can figure out how to send it inside. It's like the same the company has a mailroom. So in a big building, it can send a letter to Bob at this company. I don't need to know Bob's cubicle, desk number, or his office number. I just need to know Bob, and I need to know the company's mailing address. And the company mailroom staff can figure out how to get the letter to Bob. Anyways, turns out we're still running out of addresses. So this was called IPv4, and we've now switching to IPv6, which will give us much more addresses, and we'll get into that later. I digress, because now IANA doesn't exist anymore, and it was replaced by ICANN, which is called the Internet Corporation for Assigned Names and Numbers. And that's the company that decides not only so and so owns which IP address, but who owns which domain name. So if you want to buy google.com, which you can't, but you can buy some other long address, you have to pay them. And they say, well, so and so owns it, and they keep a database. Once you own it, then you can update the DNS worldwide to whatever you want. And that about covers the internet. So, any questions, leave a comment. And remember this diagram, because we're going to keep going back to this diagram in the following videos. If you watch the next video, we're going to have a cloud, which is our internet. We're going to learn more about every device here in depth, and how it actually thinks about and processes the traffic. And we're especially gonna, if you take a Cisco course, for example, CCNA, then we're gonna learn about how Cisco routers think, because there's many different algorithms for routing traffic on a router. So you're gonna think about firewalls and how firewalls think. We're not going to look too much into modems. We're going to look we're going to look at how switches think. And how, and some features of switches. We're going to look at how Wi-Fi thinks, sort of. And we're going to look at different Wi-Fi settings and security. That's it for today. Thank you.